Okay. Hello, everyone. My name is Peter. I'm a research assistant at RWTH Aachen University. And yeah, my talk is going to be about sewer networks. And maybe actually a little anecdote to that. When we had the poster session, I talked to a colleague and she asked me what I was doing. And I explained that we're working in the domain of sewer networks. And the response was, well, somebody has to do it. So I'm hoping that my presentation maybe invokes some interest for this topic, and that's why I'm determined to start with some imagery that maybe you'll find entertaining. This is the city of Aachen, so where I'm living from my time as an undergrad student. Maybe some of you actually have been to Aachen and have seen these places. And yeah, what basically happened here is multiple problems. I think we already heard in the session this morning colliding together. Meaning in a very short amount of time, we had very heavy rainfall that put pressure on our drainage networks, and we can see the consequences were felt throughout the city. And looking forward, we can expect these heavy rain events only to increase over time due to global warming. And now if we couple that with the aging infrastructure we're facing in Germany, we see that this might be a critical junction in future times. So this is why we picked this topic, because we thought it was a very practical application of the benefits of digital twin. For instance, one can assume if we have a digital model of the sewer networks with accurate information about damages or profile sizes, we can better manage the system in heavy rain events, for instance, increase capacity or maintenance work. To do this, we set up a bigger research project, and my paper tackles the topic of legacy. But since we have some time, I thought I can give you guys some context, since this is the scan-to-BIM session, and technically my paper is not so much about scanning, but more about processing legacy data. But I wanted to take the time and maybe provide some context what is happening in the scan-to-BIM. So we see we have a couple of pipelines working together to aggregate data to create a digital twin, to do hydraulic simulations and proactive maintenance. And in terms of the scan-to-BIM, our research partners in Freiburg, they built a little platform, a little robotic platform with sensors. So we have a 3D laser scanner, we have a camera ring, and it's a very compact size. You can crawl through the pipes. It directly tries to fit the laser scanning to the pipe. So depending on the profile, whether it's X-shaped, whether it's a circular profile, we try to fit the point cloud to it, and we can immediately detect deviations from what should have been the actual profile diameter. In addition to that, there's a camera ring that stitches together a view of the inner wall of the pipe, and then we can detect in a two-layer framework first anomalies, because most of the pipe usually is in perfect condition. Like damage is only a small part of the pipe. So instead of going directly into damage classification, we first want to see is there any anomalies, and then try to detect them and figure out, okay, what kind of damage are we speaking of? So yeah, and here you can see my co-author for this paper inspecting the pipe segment. I think it was in the city of Cologne. This is, I think, a very nice approach, but of course it's very time-consuming, very costly. So for instance, to scan 2 pipe segments, it took us, I think, half of a day. And so that's why we turn to legacy data, because we keep records of condition ratings for sewer networks, and we actually have a lot of information already available. Also about semantic properties like material, inspection history, etc. Plus, we can do this in basically real time. We can take entire systems, pass them through our framework, and then in real time have a 3D model that we can use to work with. Yeah, maybe some thoughts on the topic of legacy data. Somebody asked me today, why do you call it legacy data? Yeah, I think we call it that way because it was never intended with a digital twin or with a BIM application in mind. So in Germany, there is a standard how municipalities keep records for their sewer networks. This standard basically employs an XML-based formatting. And since we have this data available, we thought, hey, why not use it? Why not use it to enrich our 3D models? But of course, there are some strings attached because when this standard that describes how this data is organized was developed, it was not with a BIM or with a digital twin use case in mind. So let me give you a brief overview of what's happening in this pipeline here. So basically, we have our inspection data, and in the first step, we try to generate the geometry. So the inspection data is structured by the pipes or the nodes, and the pipes have coordinates, they have sizes, they have diameter information, and we try to extrude a geometry of the pipe. And then in the second pipeline, we try to integrate semantics and also inspection history and possible damages. Now, why did we split the pipeline? And you could possibly argue, why don't keep it concise together? That was because we wanted to enable basically a second layer for input data. So imagine we could derive the geometry from the legacy data, but we could also use the scan data that we just acquired, and then use the information we have on semantics and inspection history to enrich that scan data. So that's why we decided to split this approach to enable more versatility. Yeah, so the first step was extruding the geometry, and in the second step, then enriching the semantic information. For the challenge there is now that we can how to map the semantic information to the geometry in such cases where we didn't generate the geometry from the legacy data itself. So you can imagine if we use the same legacy file that I showed earlier, there is codes, there is names, we can match them, and we can establish a mapping relationship. In a scenario now where we take a geometric model from laser scan, of course, we do not have this information. Also, more often than we like it, legacy data is not 100% nice or clean to work with. So that's why we developed a spatial mapping technique where we basically try to establish an index tree based on the centroids of the pipe, and then try to map them based on their spatial proximity. So when the inventory pipe described is in a spatial relationship with, for instance, the pipe that we got from the scan data, then we know that there is a relationship, and we can map the semantic data and also the inspection data. Yeah, let me show you the results. So here we see a segment that we passed through this pipeline. So in the background we see with the pipe network, the semantics are now mapped to the individual pipe segments. Plus we can insert damage markers. So side note, we used IFC OpenShell as a library to generate these models. And yeah, the name-based matching, as we could imagine, worked very well. So we have a very high accuracy here. For the spatial matching, I think we could, out of 101 pipes, only 17 could not be mapped. I'm going to talk about it a bit in the limitations. Yes, and then we also did some validation through the building smart validation service. Plus, we flagged any mapping issues, so where we could not establish a link between geometry and semantics. So an engineer could look at it and maybe decide for themselves how to map that data. Yes, I mentioned before some limitations with this approach. I think the overarching limitation is that this legacy data was never meant to do that. So we're doing that because we have it readily available and we wanted to use it, but we are a bit abusing it in that sense. And so one issue, of course, is how it handles curved pipes. So curved pipes are mostly presented in the legacy data, for instance, with 3 or 4 coordinates. Thus, you can imagine that our approach of calculating centroids and then doing a spatial mapping here created some issues. That's why these 17 pipes that we, for instance, couldn't map correctly. Yeah, some outlook, where do we want to go with this? My colleague who also worked in this project, but in Professor Smarsley's group in Hamburg, gave a nice speech about this in the morning. So the idea is that we can now also use this data to create knowledge graphs. So we developed an ontology, we can populate a knowledge graph, we can link it with the model, and then basically create a platform that provides a nice surface for engineers to work with, to have visualization of potential damages, but maybe also to interact with chatbots, for instance, to query for certain types of damages. If you were in the session this morning, you could hear my colleague Sabine talk a bit about his ideas for this topic to come. So that concludes my presentation. If you have any questions, I'm gladly to answer them, and thank you very much.